All right. This week we're going to be talking about power analysis and effect size calculations. All right. This is our objective. We're going to examine the factors that are important for determining a power analysis and effect size. And my goal this week is that you guys will have a better understanding of these concepts. And later in the lecture, we're going to go over some examples so that you can be familiar with when you're reading a research article, how to interpret and critique the sample size calculations from a study. All right, just like with other weeks, I have some videos and readings for this week. You guys may recall, you may have seen some of these videos earlier in the semester. I think it's helpful to reinforce these concepts and go back over them. These are very short, easy to understand videos that I think will help you better understand these concepts. All right, so let's review a few concepts before we get into the meat of the lecture. So descriptive statistics is when we're organizing, summarizing, and displaying data. Typically that's done with tables, charts, averages. As you're reading a research manuscript, usually the first table that you see is a what I might call their table 1, which are usually their descriptive statistics that may be summarizing differences between the groups. Now they may use some inferential statistics just to show differences in, say, those initial descriptive statistics to show that the groups are equivalent. But when we're using inferential statistics, that's where we're using sample data to draw conclusions about a population. So you're going to see later in this lecture that as you read over those manuscripts, they're going to present some inferential statistics and trying to make some inferences about a population. You have to remember that sometimes the population, the sample that is drawn from the proposed population in anesthesia, the sampling methods in many anesthesia studies utilize a convenient sample. And so sometimes generalizability can be difficult to the larger population. Now, confidence intervals, specifically a 95% confidence interval, is a range of values that you can be 95% certain that the true mean, and it includes the true mean of the population. Bottom line is, if you have wider intervals, you have lower precision. And so you're going to see a larger spread. Say for this example, this shows from 75 to 125. Whereas if we go to a large sample size, we have much better precision to make a point estimate. And you see here, it's right around the mean of 100, and so it's a very tight interval when you have a larger sample size. So we can be very confident that that value lies within that range. So we've talked about the null hypothesis, and in research studies and inferential statistics, what you're trying to do is to disprove the null hypothesis. The null hypothesis simply states that the means there's insignificance or no relationship between two variables. So if we reject the null hypothesis, then we accept the alternative hypothesis, which is that in fact we are rejecting that, and that there is a significant difference between the groups. If we have a p-value less than 0.05, so it's statistically significant, we reject the null. If it's greater than 0.05, and we're going to talk about that here in a moment, then we fail to reject that null hypothesis. The other important piece that goes along with inferential statistics and hypothesis testing is the type of hypothesis test we use. Either a one-tailed or a two-tailed test, say a one-tailed or a two-tailed t-test. If we're using most people, if they're using a two-tailed t-test, which means we're not saying the direction of we know there's a relationship, but we're not specifying at the outset where it is. So the bottom line, what that does is that actually increases the sample size that you need, because it's dividing, because instead of say needing, if you do a one-tailed t-test, you've got about a 5% is all over here chance, whereas here you got 2.5% on this on either side of the probability distribution, and so you'll need a larger sample size with that, and you'll see an example later. Hypothesis testing. As I mentioned, we're trying to reject the null hypothesis and accept that alternative. So say, for example, our null hypothesis in this one is that drug X does not decrease post-op pain. So in this, if we said it does not increase and we don't find a difference, it means our finding is falling somewhere in this middle area. Or our alternative hypothesis is that drug X does decrease post-op pain, in which case we may get a probability distribution that's in this range here or over here. And so say, for example, be less than 0.05. So to test the null hypothesis, we choose an appropriate statistical test which has a test statistic which it is derived. T-tests have a t-distribution, which is what this looks like. A chi-square is going to look like this type of a distribution. And then F-test, which is an ANOVA, where maybe you're comparing two or more groups, is something that looks like this. In each of them, they obviously have their own sampling distribution. And each value of the test statistic will be associated with a certain probability of meaning a p-value. And there again, if we get a p-value less than 0.05, we reject the null hypothesis, as you might see in these areas, and we accept our alternative, that there in fact is a difference between the groups, or there's a relationship between the groups, or an association. What is a p-value? This is called our level of significance, and we've touched on this. This is throughout the course. So if the probability of a type 1 error is 0.05, this means that there's a 5% chance that the observed finding is not true. The p-value is influenced largely by the sample size, meaning larger sample sizes, you have a greater chance of finding a difference. But with very large studies, sometimes you can find clinically, statistically significant findings that are clinically irrelevant. Whereas in the contrast, small studies can find non-significant findings that may in fact be clinically important, but they also may be due to chance. And that's why sometimes we end up seeing studies, whether they're replicated, and sometimes they're with larger, that we have to confirm, and maybe we have a larger sample size, and later on maybe we're able to find those differences. Power is a probability that the test will reject a null hypothesis correctly. And the value ranges from 0 to 1. So what is the probability of a type 2 error? Well, that's 1 minus power, and that is called the beta error. The beta error is typically set at 0.2 or 20%, meaning you have your power is 80% probability to detect the differences. As power increases, the chances of a type 2 error decrease. And with larger sample sizes, you have more power, and with small sample sizes, you have less power. So here's an example. So here we have power as a function of effect size and sample size. And this is using comparing two proportions. Say we have an effect size of 40%, 50%, 60% difference between the groups. So if we look here at the green line, which is probability 1, the smaller effect size, you can see here to achieve that we can't get past just above 60% with 200 subjects with this example. However, when we look at a p-value of 0.5, we're achieving over 80%, we're getting 80% power and a sample size of probably 60. And then here, with the larger effect size, what we do is we get up here and we're not needing very many, maybe 30 people, or actually even 25. Also, what you see is with increasing power, the curves start leveling off. So increasing the power doesn't do much more other than increase the cost of the study. So it doesn't have much more value added at above 80%. If we look over here at these different effect sizes and different sample sizes here, so we have a sample size of 7 and a sample size of 10. So for an effect size of a mean difference of 1.33 between two groups, here you can see with a smaller sample size, we only have an effect size of about 60%, a power of about 60%. However, we achieve 80% power with that same effect size. Now, if we go with the same sample size of 7, we would need to have a much larger difference between the groups to achieve the same equivalent power.